All right, welcome back. We're going to take a look at this next lesson on exponential growth and decay. It's chapter 10.6. This is part 1. We need to do a little review, and we talked about this, I think, in the first session. This basic formula for exponential growth and decay looks like this. And if you recall, everything had meaning here. A was the initial amount. Y was that future amount. B is the rate, and we call it the base. And X is typically talks about time. Now we're going to be building on this particular basic formula, and all the formulas you're going to get today are based on this same formula here. One of the things we do want to mention as we dig in again here is that we're going to talk about growth. And in growth, the base has to be greater than 1. And in decay, the base has to be between 0 and 1, a common fraction. So let's take a look at the first formula for these story problems. All right, the first formula on our list here today is to take a look at this one. It involves E. And you notice how similar it is to our basic, the raw formula here. But what is different is that the base has been substituted with this e to the k business. This combination of this natural number, Euler's number, that occurs in nature, and k is serving the function of a single base down here. Something to kind of make a note of. This is a form that scientists tend to prefer. So let's do a problem like this, and we usually use a problem like this when we have two ordered pairs in the problem. So let's do a problem with population. How about in 1980, the population was 37 million, and in 1985, the population was 62 million. Now, this is going to be done just like we've done earlier a couple of days back. Well, we can, if we let this first date, the earliest one in time, be 0, and that makes this one 5. If this is 0, then that has to be my initial amount. So we could fill that in. The initial amount is 37, e to the k, and then the other letters are t and y here. Well, we can get those two letters from the x and y coordinates. Here's your time, and here's your y value. We can stick those in here. 62 is my future value in 1985, and that would be 5 years from now. So there you go. We can solve this problem. It only has one variable. It's k. E is not a variable, by the way. It's just a number. So we're going to solve this, and we're going to have to do it by using logs. So let's start by dividing both sides by 37. And I get this fraction. I'm going to leave this as a fraction so I don't have to round it and kind of affect the accuracy. E to the 5k. Just turn those two around. Now, in order to solve this, we're going to have to take the log of both sides, and the natural log would be the natural one to use here because I've got a base e. So natural log base e of 62 over 37 is equal to the natural log base e of e to the 5k. Well, as we've been discussing all along here, when we see an exponent here in the result, we can drive it around to the front, and in this case, this all becomes 1 and just goes out. So we got natural log base e of 62 over 37, and that 5k came around to the front and is multiplied times this, which is just 1. I don't really need to show that because natural log base and a base undo each other and become 1. So I don't need to show that. Now we're going to divide both sides by 5 here, and we can use our calculator to come up with the answer on this. Okay, so I've entered that in the calculator, and once again you notice that the calculator does not show us that e. And also, once again, I'm gonna leave this as a fraction so that my accuracy is not compromised. Be careful if you round in the middle of a problem, you're compromising your accuracy. I didn't need any other parentheses in this because of the order of operations. What do we get? Well, we get a number. It's 0.10324, and that's equal to this thing called k. Now, k is not the rate. The rate is this combination of e and k. The rate is this combination of E and K. So if I wanted to write a formula here now using this, I would go back and write the original initial amount, 37, e to the 0.10324 times t. There's my equation for this problem. And it's got the initial amount in here, and it's also got this E-K combination that shows me the rate. Now what if the problem goes a little further and says, what would the population be in, say, 1995? Well, 1995, that's 15 years after 80, so that's year 15. So we're going to just take and stick 15 in here, and let's see what we end up with. All right, here's my answer to that question. What if it was 15 years later and I put a 15 in here for t? You'll notice that instead of inserting k in here by rounding it, I've used the answer button so that my number is actually much more accurate because I didn't round it. This is something you can consider doing, using the answer feature. That's your second negative button. And if you use the answer button, your answer will be far more accurate. Let's see what we ended up with here. Turns out it's about 174. So we find out that the population in 1995 would be 174 million. And the accuracy is improved by the fact that instead of putting this number in, I've used the answer button. A little trick for you to use to keep your answers accurate. All right, let's look at a different kind of formula here. All right, let's take a look at this formula. There's actually two here, but you really only need to pretty much remember one with a little exception there to it. This is the formula similar to the one we did before on finances, where we're going to take a percent. This is a problem where you use it whenever you have percents in the problem. And you're going to stick the percent right in here for R. Now, let's say I have 6%. I would type in here the decimal, 0.06. And it's being added to 1. And the reason for that is it's automatically adding the original 100% of the original amount. Okay? So this is a growth problem, and it's clear because there's a plus sign here. Remember, growth, the base has to be greater than 1. And if I put a decimal in here, it will be greater than 1. Okay? On the other hand, decay has a minus sign here. So if I put a decimal in here and I subtract it from 1, I will get something less than 1 here. That's because the base here has to be between 0 and 1, decay. Now these two formulas are so similar, you really only need to know the basic form and then just recognize, oh, it's a plus sign if it's growth and it's a minus sign if it's decay. Or let's try a problem from your book, example 1 on page 560. All right, again, this is problem example 1 on page 560. Now the problem talks about a cup of coffee. Coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, it's eliminated. Oh, that sounds like something's getting smaller. So this is going to be decay. At a rate of 11% per hour, how long will it take for half of this to be gone? Okay, so I'm going to use the problem with decay problem, and also because it's got a percent, I notice I'm going to use this formula, 1 minus R raised to the t, and it's got everything I need. I can put the initial amount in here, I can put the percent in here, and we'll talk, and t is what I need to find. We'll talk about how to find y. So let's put this in here. The original amount was 130 milligrams. The percent is 11%. Let's write it as a decimal, 0.11. We don't know how long, that's t. And the number out here has to be half of the original amount. So we'll just have to do the arithmetic on the side and say, oh, that's got to be 65. Half of 130 is 65. Okay, now if we're going to solve this, of course, because this has got an exponent up in the variable up in the exponent, we're going to have to use logs to solve this. But before we do that, let's divide both sides by 130, and we end up with a decimal or a fraction here, 1/2, 0.5. These are going out. And this base now is 0.89. Well, that makes sense because the base is less than 1. It's got to be decay. This is a decay problem. So in order to solve this, we're going to have to take the log of both sides. I'm going to use log base 10. I'm not going to write the 10 this time. Log base 10 of 0.5 and log base 10 of 0.89 raised to the t. I did not write the 10 here this time, but this is the common log we're using. Now, if I have a result raised to a power, I can drive that around to the front and multiply. Powers of power says I'm going to multiply the exponents. So this is log of 0.5 equals t times log of 0.89. Now I'm going to have to divide both sides by log 0.89. I'm going to do that, but I need to move up on the page. All right, well, I've continued on up here at the top. In order to get the variable alone, we're going to have to divide both sides by log base 10 of 0.89. Log base 10 of 0.89. Of course, I'm not writing the 10s there. T is now alone because these have gone out. Let's use our calculator. All right, I've punched that in. I just want you to notice here that I've closed the result here, 0.5, close the percentage. If you don't do that, you'll end up with something that's not quite right. You've got to, it opens the percentage for the parentheses for you. You've got to close that parentheses. And I've done that now. So here we go. The answer I get is about 5.95. 5.95. So this t is 5.95. Well, what was the question asking? It was asking how long would it take for that caffeine to dissipate in hours. Well, this is about approximately 6 hours for that half of the caffeine to dissipate. This looks a little bit like something we're going to talk about in the next episode called radioactive decay and what's called the half-life. But this is just a kind of an introduction to that. But you notice the formula that we used gave us a percent, so we were going to use the formula that would accept a percent. All right, let's look at something else here. All right, let's take a look at this one. This is problem 4 from your book on page 563. And this is using that formula where we have e to something. Now this looks a little different than what you've seen before. Let me rewrite it so that it looks the way you're used to seeing it. K here is actually a negative 1 over 250 and then times t. Negative 1 over 250. So now you can see that k is a negative and t is still here. Now what we need to point out here is that if this exponent is negative, that means that this is a decay problem. We'll review that again later. It's going to be decay. And let's see what the problem is asking. It says a radioisotope is used as a power source for a satellite. The power output, P, in watts, is given by this formula, where T is the time in days. Is the formula for power output an example of exponential growth or decay? Well, it's decay here, and the reason for that is this negative exponent causes this to actually flip over 1 over e to that power. So this has now created a number less than 1. And so if the exponent is negative, we have a decay problem. Question number 5 asks the question, find the power available after 100 days. So let's go ahead and put that in there. After 100 days, we don't know the power, but after 100 days, that would be negative 100 over 250. Now again, the exponent is negative here, so I'm expecting decay. And I can use my calculator straight away on this. All right, you can see I've entered it in the calculator there. 50 was our initial amount. E to the negative 100. Make sure you have you use, if you got parentheses on your calculator, use them properly there. This exponent is negative. Let's see what we end up with an answer. 33.5. 33.5. So the power output is 33.5, and that's in watts. Okay, 33.5. Well, what happened here? Well, it went down, and the reason it went down is because this is a decay problem. What happens is the power deteriorates in the spaceship or the satellite or whatever it is, it deteriorates and it goes down. So this underscores the fact that if this exponent is ever negative, that means that you're going to have a decay problem. Let's summarize that. All right, let's kind of summarize. You've got basically 4 formulas, but in reality, there's really only 2 here. These on the left are growth, and these on the right are decay. Growth, you can tell, is going to be growth because this base now will be greater than 0. The base will be greater than 0, and over here, you can tell that this is decay because the base will be between 0 and 1. So just memorize one of those formulas and realize that the sign in the middle tells you whether it's growth or decay. Now this other formula, using E, if this exponent ends up being positive, you're going to have growth. If the exponent ends up being negative, you're going to have decay. So the 2 formulas are very useful. The scientists like to use this one. When do you use these? Well, this one is used when they give you a percent in the problem. And you put that percent right in here for R. This one is used more often when you have 2 ordered pairs in the problem. They'll give you an ordered pair with a date, a time, and a y value, a time and a y value. So it might be like t and y, t and y. And if this first one happens to be 0, that's your initial amount A. So you stick that right in here for A. Set the first one equal to 0, and that becomes A. Then the other ordered pair goes right in here. So when you have ordered pairs are very useful to do this second formula. So you really only have 2 formulas to memorize here. Just recognize that these over here in decay have minus signs involved, and the ones with growth are positive. Let's take a look at your homework for tonight. All right, so here's your assignment for tonight. And I'm also going to put up there tomorrow's assignment. This assignment tonight's not that long. It's 4 through 11. I've already done 4 and 5 for you. But you can go ahead and start this next one too if you feel like you can go ahead on that. You have all the information you need. However, tomorrow I am going to give a little discussion on radioactive decay and half-life. This is about calculating the half-life of substances and carbon dating and so forth. But give that a tackle tonight, and I'll talk to you next time. Thanks.